Welcome back to the session. In this class, let me explain another concept in the lesson, electrostatic potential and capacitor. That concept is equipotential surfaces. The next content is equipotential surfaces. Equipotential surfaces. As per examination is concerned, another important concept for your examination, many times definition of what? Equipotential surface is asked in the examination. See, look at the title here. Title itself will give the definition of what? Equipotential surface. Equi means same. Any surface which is having same electrostatic potential at every point. If you consider any surface, calculate the electrostatic potential at all the points on the surface. If the value of electrostatic potential is same at every point on the surface, then such a type of surfaces are called equipotential surfaces. Let me write the definition here. What is the definition of equipotential surfaces? Surfaces having same electrostatic potential. Same electrostatic potential. Electrostatic potential at every points. At each points. Each points are called equipotential surfaces. Are called equipotential surfaces. So you consider any surface, that surface is said to be equipotential surface provided all the points on that surface should have the same value of what? Electrostatic potential. If that condition is satisfied, then the given surface is said to be what it is? Equipotential surface. See, for example, if I consider single point charge. Consider a single point charge. This is the single positive point charge. When you consider single positive point charge, imagine a sphere of a radius r around this charge. Let me imagine a sphere of a radius r. Let me imagine a sphere of a radius r around this charge in such a way that this charge is at center of the sphere. Okay, whatever the sphere you are going to imagine here, this sphere for this charge is said to be what? Which surface? Equipotential surface. Why it is said to be equipotential surface? So if you determine the value of electrostatic potential at each points on this sphere, the value of electrostatic potential is same or else it is constant. If I ask, if R is a radius, if R is a radius of this sphere, if I ask what is the electrostatic potential at this point, the electrostatic potential at this point is given by V is equals to 1 divided by 4 pi epsilon naught. If Q is a charge, then what is the value of potential on the surface? The potential on the surface is given by V is equals to 1 divided by 4 pi epsilon naught Q divided by R. So whatever the points you consider, all points are symmetric to the charge. All points, whatever the points I am considering on the surface, all points are symmetric to the charge. So at all the points, if you determine the value of electrostatic potential, that electrostatic potential at all the points on this sphere is the same, and its value is given by 1 divided by 4 pi epsilon naught q divided by r. So this surface is said to be, which surface it is? Equipotential surface. You imagine one more surface here. Say for example, this is another surface. If you imagine one more surface here, and this is also called equipotential surface. So if we calculate the value of electrostatic potential, a value of electrostatic potential on this surface, you calculate all the points of this surface. Once again, they have the what? Same value of electrostatic potential. If smaller is a radius of what? This sphere, then what is the electrostatic potential here? V is equals to 1 divided by 4 pi epsilon naught q divided by smaller. So this is called first equipotential surface for a charge. Which charge it is? Point charge. This is what? Second equipotential surface for a what? Same charge. This may be what? Third equipotential surface for what? Same charge. If a given charge is a point charge, then equipotential surfaces are concentric spheres. What is the nature of the equipotential surface? What is the nature of the equipotential surface for a given point charge? For a given single point charge, the nature of equipotential surface is a concentric sphere. If you keep on drawing what? Concentric spheres on that sphere, whatever the sphere you consider, all the points on that sphere having same value of what? Electrostatic potential. Then such a surfaces are called what? Equipotential surface. So this is the one example for what? Equipotential surface. So let me write the example here. What is the example? The first example what I am taking here, example 1, for single point charge. Single point charge, number of concentric spheres are the which surfaces they are? They are equipotential surfaces. They are the equipotential surfaces. So if you take the single point charge, around this single point charge, if we imagine the number of concentric spheres, these number of concentric spheres are the examples for the equipotential surface. This is first equipotential surface, this is second equipotential surface, this may be a third equipotential surface. These are the number of equipotential surfaces for a single point charge. Suppose if we consider horizontal uniform electric field. Suppose if we consider horizontal uniform electric field. First note down the first example for equipotential surface. Let me consider the second example where I am going to draw equipotential surface for uniform horizontal electric field. So this is the equipotential surface for single point charge. This is the nature of equipotential surfaces for single point charge. In the next case, I will consider the number of equipotential surfaces for a horizontal electric field. So let me consider the second example here. Example 2. So the second example is for horizontal uniform electric field. Uniform electric field. Equipotential surfaces are planes, and those planes will be perpendicular to the direction of what? Electric field. whatever the planes you are considering, all those planes are perpendicular. Plane of the planes is perpendicular to the direction of what? Electric field. Let me draw equipotential surface here. So these all are equipotential surfaces here. Let me draw the equipotential surface for horizontal uniform electric field. I am taking horizontal uniform electric field. Let me consider horizontal uniform electric field. So what is the nature of the electric field here? The nature of the electric field is which type of electric field it is? Horizontal uniform electric field. What electric field I am taking? This electric field is a horizontal uniform electric field. For this horizontal uniform electric field, the nature of equipotential surfaces are the planes. These are the planes here, and those planes are the which surfaces? They are equipotential surfaces. These planes are equipotential surfaces. First equipotential surface, second equipotential surface, third equipotential surface. If we calculate the value of electrostatic potential at all the points on this surface, that will be constant. Therefore, for horizontal uniform electric field, this is the direction of one electric field. For horizontal uniform electric field, the equipotential surfaces are the planes in such a way that those planes are perpendicular to direction of what? Electric field. And one more point to concentrate here, direction of the electric field. Look at the direction of the electric field. The direction of the electric field is always perpendicular to what? Equipotential surface. What is the direction of the electric field, you tell me? The direction of the electric field is always perpendicular to the equipotential surface. So that point should be concentrated here. What is the nature of equipotential surface? The equipotential surfaces are such a way that the electric field is always perpendicular or normal to the equipotential surface. So this is what the second example where I am considering the nature of equipotential surfaces for horizontal uniform electric field. Now I am concentrating on few important properties of what? Equipotential surface. In the next the part, let me explain some important properties of equipotential surface. So write on the next one. Equipotential surface properties. That is properties of equipotential surface. Properties. Very important. First property. So very important property of any equipotential surface, the work done in displacing point charge from one point to another point on equipotential surface is zero. If you take a charge, displace that charge from one point to another point on equipotential surface, the work done in displacing that charge is zero. That is very, very important point which is related to what? Equipotential surface. What it is? First property, work done. Work done in displacing charge on equipotential surface is 0. There is no work done when you are displacing a charge from one point to another point on equipotential surface. Will you tell me what may be a reason? What may be a reason? See, for example, this is equipotential surface. For which charge it is? Single point charge. Imagine that I have 2 points on the equipotential surface. Okay? I am displacing the charge from first point to what? Second point. First point to second point on which surface? I am displacing a charge on equipotential surface. If I ask, what is the work done in displacing a charge? What is the work done here? The work done is given by which charge you are displacing. Say for example, you are displacing a charge, say Q1. Which charge you are displacing multiplied by potential difference between the 2 points from where to where you are displacing the charge. Then Q1 multiplied by what? dV. What is dV here? dV is a potential difference between the points 1 and 2. What is potential difference between the points 1 and 2? The potential difference between the points 1 and 2 is given by, it may be V1 minus V. V1 minus V. But what is equipotential surface? The surface having same value of electrostatic potential at each point. Means electrostatic potential at point 1 is equals to electrostatic potential at what? Point 2. Point 1 and point 2 are of same potential. When the 2 points are of same potential, V1 minus V2 or potential difference dV will be 0. Why the dV is 0 here? Because 2 points are of same potential, because it is equipotential surface, therefore the potential difference is 0. If potential difference is 0, the work done is 0. Therefore, what is the first property here? Work done in displacing charge on equipotential surface is 0. Shall I write second point here? Extension of the same. Potential difference. Potential difference. Difference between any 2 points. Between any 2 points. Points on equipotential surface. On equipotential surface is 0. If you calculate the potential difference between any 2 points on the equipotential surface, the potential difference is 0. Why the potential difference is 0? Because the 2 points what you are selecting, they are of what? Same potential. When the potential is same, the potential difference is 0. When the difference is existing, the 2 points are at a different potential, then the potential difference is existing. If the 2 points are at the same potential, definitely the potential difference is 0. Therefore, whatever the potential difference you determine between any 2 points on the equipotential surface, that potential difference is 0. Already I discussed the third property. What is the third property? Electric field is always perpendicular to. Electric field is always perpendicular to equipotential surface. The direction of the electric field is always perpendicular to equipotential surface. We have seen in the case of what? Second example. So this was the plane, that is equipotential surface. What was the direction of the electric field? The direction of the electric field was like this. Means the direction of the electric field is perpendicular to which surface? Equipotential surface. What is the third property here? Direction of which field? Electric field. Electric field is perpendicular to which surface? Equipotential surface. Equipotential surface. surface. So this is the third property of what? Equipotential surface. Then which one is the fourth property? If we consider number of equipotential surface for a given charge, if we consider the number of equipotential surfaces for a given charge, the equipotential surfaces never intersect each other. They never intersect each other. Equipotential surfaces are very close to each other in the region of strong electric field. Equipotential surfaces are very close to each other in the region of strong electric field, and they are far or well separated from each other in the region of what? Weak electric field, whether they are far, whether they are close to each other, but they never intersect each other. Then what is the fourth property? Equipotential surfaces. Equipotential surfaces never intersect. Never intersect. So whatever the equipotential surface you consider, the equipotential surfaces never intersect each other. You can add one more property to what equipotential surface, that is the last property. Which is the last property? Equipotential surfaces are very close. Equipotential surfaces are very close in the region of strong electric field, and equipotential surfaces are very far from each other in the region of what? Weak electric field. The number of equipotential surfaces are crowded together or they are very close to each other indicates that there is a strong electric field. So this is about the properties of what? Equipotential surface. The properties of what? Equipotential surface. Let me draw the nature of equipotential surface for electric dipole and for two equal charges. You know very well what is electric dipole. Electric dipole is a system consisting of what? Equal and opposite charge. And I will draw the what? Nature of equipotential surfaces for equal and opposite charge, that is for electric dipole, and I will draw the nature of equipotential surface for two equal positive charges or two like charges. Okay. Dear students, look at the nature of equipotential surface for electric dipole. Electric dipole means it is a equipotential surface for equal and opposite charges, that is unlike charges. The second diagram, it is a equipotential surfaces for two like charges. What difference you are noticing? For unlike charges, between the charges, the electric field is strong. For unlike charges, between the charges, the electric field is strong. That's what the equipotential surfaces are very close to each other. Look at the equipotential surfaces between the charge. Between the charges, the equipotential surfaces are very close to each other, indicating that between these two charges, the electric field is very strong here. But for like charges, look at the region between the charges. The equipotential surfaces are well separated from each other. They are far from each other, indicating that between the like charges, the strength of the electric field is weak here. Here the strength of the electric field is weak, and here the strength of the electric field is very strong. So these are the nature of what? Equipotential surfaces for different charge system. Okay.